which is nothing too complicated. It's literally just an equation with a derivative in it. And things that we did with it, it was kind of like a hodgepodge of stuff. But we mainly just started kind of like analyzing it. And one way that we can analyze a differential equation is with like a slope field. It basically represents all these possible slopes that could be on the original function. And we had ended, so I skipped the approximations, which we might get to today. We talked about how to tell like when a function was, like when would it be increasing? Because we know that the derivative does inform us about increasing and decreasing. And then the second thing that kind of relates to is like, well, can we talk about the concavity? And yes, we can talk about the concavity, but before we do that, if you are following along in OneNote, these notes were shared with you at the very bottom of the page, but it's implicit differentiation. Those of you who had me first semester, like I did just kind of copy and paste over a few slides. This was taught in Unit 3 at the very end of it. Do want to review it again because it is, again, important for this unit. So I was going to kind of start off with just like the basics, and then we'll see how it connects to what we're doing in this unit. So implicit differentiation is a way that we are going to integrate, and there will be some certain circumstances that we need to use and know when to use it. So when we say take the derivative in calculus, we often aren't very clear about like what we're taking the derivative with respect to, because often it's going to be implied you're taking the derivative with respect to x. So like another way to kind of say the derivative and make it a little bit more clear is we use like this d dx notation. That symbol is kind of like an operation. That tells you to take the derivative. So there's nothing like to do with that. What is important and what is often left unsaid is that dx in the problem means you're taking the derivative with respect to x. Well, if we're taking the derivative with respect to x and we have an x, there's nothing different. Like we know how to do that. The derivative of x squared would just be 2x. Like we know that, it's true. We know how to take the derivative of that. Cool, they're both. So derivative of x squared, sorry, my pen had died, 2x. Same thing with this one on the bottom. We don't normally look at the derivative this way, but if I say d dy, that means we're doing it with respect to y. Well, if I have a y squared, nothing to do differently, its derivative would just be 2y. Where we have to do this thing called implicit differentiation is when you're taking the derivative with respect to a variable, and you have a different variable. So looking at this bottom one, this would be one where we have to do the derivative with respect to something else. It says d dx, so we are taking it with respect to x, but the function we have is in terms of y. How implicit differentiation works is it is kind of an application of the chain rule. Those of you who had me first semester, I hope we kind of remember the process, but you take the derivative as normal. So the derivative of 2y of y squared is 2y, but then you have to have like a little fixer piece multiplied after that. And how did we do that? Multiplied, we said dy, because that's what we had, over d what we wish we had. We wish it was an x. So that would be the derivative of that with respect to x when we have something in terms of y. I could go deep into the theory about why we do that. The short version of the answer is y is often some function in terms of x. So it's kind of like there's an x inside that function. So we are kind of doing like the chain rule. So go ahead and look at, we'll start with this example. Implicit differentiation, again, we'll eventually see how this connects to this unit, is often used when you're taking the derivative of functions that have both x's and y's in the problem. These are often, I said functions, that should be more clear. These are often not functions. They often fail the vertical line test. So things like circles, ellipses, spirals, weird looking curves. And we're going to take the derivative with respect to x. Now, if I just said take the derivative and I left off that statement, it would be implied we're taking it with respect to x. So if I'm looking at this one, the 3x squared is fine. I'm taking the derivative with respect to x, and I have an x, so it would be the derivative as normal. Sine of y, that has a y, but we're doing it with respect to x. So you would take the derivative normally. The derivative of the sine of y would be the cosine of y, and then multiply it by the fixed piece. So I think d, I had a y, over d, I wish it was an x, and I'm taking it with respect to x. That would be a differential equation. It's an equation with a derivative in it. How this kind of attaches to this class is normally, or this unit, we would say, hey, what's the first derivative? We know that's what dy dx is. Well, when I divide both sides by cosine of y, that looks like something we would use a lot in this unit. Like I could make a slope field with that, or I could interpret it in several different ways. Questions so far? Try these two examples for me. And those of you who had me first semester might recognize them because they're the same, but go ahead and retry them again. Take the derivative with respect to x, and then we'll build up and see how this connects to some of the other stuff we've done. And again, any derivative rule you've learned can kind of show up with this with this topic.
Do you want us to solve for?
Don't worry about solving for dy dx. Because honestly, in this unit we're in, like it will often repeat by itself. And again, you only really need to do this kind of action of implicit differentiation when you're taking the derivative of a variable that's different from the one you're taking it with respect to. So if I'm looking at this first one, taking the derivative, I'm taking it with respect to x. So the sine of x is fine. The derivative of the sine of x would just be the cosine of x. The derivative of the sine of y, this would be implicit differentiation. The derivative of sine is cosine of y, then we multiply it by the fixer piece. I had a y, I wish it was an x, and then equal to, here's another one, y squared. Taking its derivative will be 2y, but again, multiply, I had a y, I wish it was an x. Could solve for dy dx, but again, that would just be algebra and no longer kind of like the calculus. Looking at this second one, what rule would you need to make sure you're using? The product rule. This is sine of x times the sine of y. So you would want to make sure you use the product rule. If you need a reminder of the product rule, so we have the first times the second. Its derivative I think of as like the first times the derivative of the second plus the second times the derivative of the first. Again, that word doesn't matter since you're just multiplying and adding. So finding the derivative, I have the first times the derivative of the second. The derivative of the sine of y would be cosine of y, implicit. So I had a y, wish it was an x, plus the second times the derivative of the first is x, so good as is, and equal to an implicit one, 2y dy dx. Some students mess up where they fit the dy dx. Remember, as soon as you take the derivative of y, you multiply basically by dy dx. And again, you might have had those first two terms flipped around, but it would have been equivalent. Last one, and then we'll look at the second derivative. I have the sine of x times y. Oops. What rule or rules we need to make sure you use for that one in addition to implicit? Chain rule and the product. So basically you'll have like the product rule within the chain rule. Try that one. Again, don't worry about simplifying it. And then we're going to move into the second derivative implicitly, and then eventually see how all this connects implicitly. So we said it's a chain rule with the product. So again, when I do the chain rule, we take the derivative of the outside. The derivative of the outside would be cosine. Leave the inside the same. Then we have the chain rule times the derivative of the inside. And this is where that product rule is going to come into play. So what's the derivative of the inside? I have the first times the derivative of the second. The derivative of y would be 1, but then we had a y, I wish it was an x, plus the second times the derivative of the first. And then what is that equal to? Well, the derivative of y squared would be 2y. Again, I had a y, I wish it was an x. Yes. You would want it in parentheses because that cosine part would have to distribute to both of them technically. So you would want it in parentheses. So one more kind of review. Let's look at this example and then we'll kind of use this to kind of merge back into Unit 9 material. So I have for x squared plus y squared equals 36, we want to find the second derivative. So again, this notation, it just means the second derivative. I don't pronounce it any differently. I just kind of look at that symbol and know it's the second derivative. Anyone remember from pre-calc or even earlier, what type of graph is x squared plus y squared equals 36?
Circle.
It's a circle. So basically we're finding the second derivative of a circle. Well, before we can find the second derivative, what do we need to find first? The first derivative. This is where the implicit kind of comes into play. The derivative of x squared is going to be what? 2x. The derivative of y squared is going to become 2y dy dx. And then 36 is going to become what? 0. So we took the derivative. In this, like we do want to find the first derivative before we go and find the second derivative. Well, what is the first derivative? Dy dx is the first derivative. So if I want to solve this for dy dx, I can imagine subtracting 2x from both sides and then dividing by 2y. So what is the first derivative? The first derivative of a circle is negative 2x over 2y, which is probably a whole lot easier to simplify and say the first derivative of a circle is the negative x coordinate over the y coordinate, which is actually very similar to the differential equation you see in homework 1. It's just kind of the reciprocal of that flipped around. So then once we know the first derivative, we do want to use that to find the second derivative. I like this one because it does pull up a whole lot of review to kind of do stuff with. When I'm finding the second derivative, what rule do I need to use? It's the quotient rule. We haven't done that in a while. Not going to sing you my song, but it's the quotient rule. So doing the quotient rule, if you had Miss Kennedy, she told you, I think, some story. I don't know the story, but it's the quotient rule. And so looking at this one, take the derivative. I have low times d high, low d high, less high d low. The derivative of the bottom, the derivative of y is 1. I wish I had a y. I had a y, I wish it was an x. Draw a line down below, the bottom squared will go. And again, that's coming from the quotient rule. Evan, you had your hand up.
Yeah, I never heard this song.
You never heard the song, that's unfortunate. I'll sing the song once. I can't sing, but request to sing, maybe you need a reminder. So for those of you who had Miss Kennedy, I know she tells some story about someone looking at like God or something. I don't know. It's a weird story, whatever. So the quotient rule we know, good to review anyways for the AP exam. It's used when you take the derivative of a fraction. When I look at this fraction, I call the bottom one low and the top one high, basically. I'll say it first and sing it, but it is to the tune of Old MacDonald. So we have low d high less high d low. Draw a line, and down below the bottom squared will go. So singing it, low d high less high d low, da 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 da. Then draw the line, and down below the bottom squared will go. So that was the quotient rule. Back to our regularly scheduled notes. That is the second derivative, right? It's ugly, but that is the second derivative. Good things that we have reviewed, like implicit, we've reviewed the quotient rule. Now let's review making sure we answer our form in a way that it asks us to. It tells us to put this in terms of x and y. Right now, the second derivative is in terms of x, y, and dy dx. I'm going to go ahead and simplify it because that does look pretty messy. I don't always simplify stuff in this class, but I think in this case it does make it look a little bit nicer. Y times -1, the double negative. That dy dx is still there over y squared. We want to put it in terms of x and y, so I want to get rid of that dy dx. Well, what do I know that dy dx is equal to? Negative x over y. So good, people who had me first semester are remembering that. We know that dy dx is negative x over y. So plugging that in, I have negative y plus x. Again, the first derivative is negative x over y squared. Technically, you can stop there. That is the second derivative in terms of x and y. Let's just simplify it for fun, for the love of algebra and kind of simplifying it. What's gross about that second derivative right now? That extra fraction, especially that y in the denominator. Well, what could I multiply by that would cancel out with that y? Just another y. If I can't just multiply by y, that would change the problem, so I'm going to multiply by y over y, so that's just a 1. Make sure you distribute across to all of your terms. And so then I have a nice second derivative. Negative y times y is negative y squared. That y is going to cancel. And that gives me negative x squared over y cubed. They'll dare cancel out. Those y's that we see left over, you can't cancel across a plus or a minus sign. So there is your second derivative in terms of x or y. More fun stuff. Again, I chose this one because there's just a lot of stuff going on. Maybe those of you who had me in first semester remember. Looking in that numerator of the second derivative, what do they have in common? Squared, what else do they have in common? A negative. Since they both have a negative in common, what can we do? Pull it out, factor it out. So I have -1 y squared plus x squared over y cubed. Why would I want to do that? What is y squared plus x squared? 36. So we can actually make this a pretty nice looking second derivative of -36 over y cubed. Why might it be nice to kind of simplify that? We can easily now determine, like, I don't know, if it asks me for like the concavity, I can pretty much say, hey, whenever y is negative, the negative cubed is still negative. So basically whenever y is negative, the second derivative will be like positive, so it would always be concave up. Or if y was positive, that second derivative would always be negative, so then it would always be concave down. So it kind of helps us analyze and kind of interpret it however we need to. Why did I just take time reviewing implicit? I mean, one, AP exam, good skill to know. It does show up though in this unit. To show you where it shows up at, I went ahead, this is actually copied from my BC, their quiz from Unit 9 that we had a little bit earlier this semester. I just copied these two questions just so you can kind of see where implicit shows up in these types of problems. So we have this differential equation. Again, when we see dy dx, that is the first derivative. So it's actually going to be a little bit shorter than the one that we just did since it's giving us the first derivative. And it tells you to find the second derivative in terms of x and y. Well, taking the derivative of that problem, go ahead and do it. You have dy dx. Go ahead and see if we can find the second derivative in terms of x and y. So take the derivative, probably up to it implicitly, and then wherever that dy dx shows up at, plug what it's equal to into the problem. And then we'll see a way it's used in that number 8. And that's probably where we'll wrap up today's notes at. So again, this was a pretty easy one. No quotient rule, no chain rule, no product rule. The derivative of 2x is just going to give you what? 2. And then I have minus. Well, the derivative of y is 1, but we have a y. I wish it was an x. And of course, you could have just left off the 1 part. We want it in terms of x and y. Right now, that is in terms of dx and dy. So plugging in what it's equal to, we have 2 minus dy dx. That's fine. I'm going to go ahead and get rid of my parentheses by distributing it across. And so my second derivative is that expression. How can we use that? Like, it can help us find the concavity at a point. It might help us find relative minimums or maximums if we're using the second derivative test. For this one, how I kind of used it, it said determine the concavity of all solution curves for the given differential equation in quadrant 2. What does that mean? dy dx is the first derivative. We don't know what the original function is, but we can use the derivatives to kind of talk about what those original functions could possibly look like. So if this is my second derivative, I'm going to kind of just rewrite it quickly underneath here. We can use the second derivative to talk about concavity. We know when the second derivative is positive, concave up, second derivative negative, concave down. Well, if we are existing just in quadrant 2, which is this one, how does that information help me determine the concavity if we also know the second derivative? X is negative, so we always know that in the second quadrant, x is negative and y would be positive. So if I'm looking at this second derivative, we have 2, positive number. What would minus 2x become? Positive. X is negative, that would become positive. Plus a y, where if we're in the second quadrant, what is y? Positive. So basically, what is the second derivative in quadrant 2 always? The second derivative is positive, so the graph is concave up. So that's why I wanted to take some time to review implicit differentiation, because we often are taking the derivative of a derivative that has y in it, so we just want to make sure we have that skill. So yes, I'm already off on the calendar, but again, I am not worried about that, because to me, making sure you're ready for the AP exam and just being able to do most stuff in this unit is more important. So I did want to take today just to kind of review the implicit. So like the homework I'm assigning is not going to change. I know I got like a little bit time left in class. I do want to give you time to work on some stuff. So again, I will be here after school today. So definitely reach out to me if you need to worry about the Unit 7 or Unit 8 recovery. I'm hoping we can get all the Unit 7 recovery corrections done before spring break. For Unit 8 and then eventually Unit 9, I'm just going to say their recovery is going to be due before the AP exam. So I know it's going to get pretty busy after spring break. This unit we are in, remember there is no quiz, it's just going to be a test. Homework to work on is just going to be homework 1. Homework 1 does have a hodgepodge of topics on it. Like obviously I always want you to check your answer when doing homework, but this is like one homework where it's like definitely okay to kind of make sure that answer key is pulled up and you can kind of go back and forth, because there is a lot of stuff you might need to review, and like no 2 questions are the same. It's not a repetitive homework at all. So for that homework, this is one I especially recommend, like using the answer key to kind of get through the homework and to kind of learn from those practice problems. We'll pick up here tomorrow. There's still a few more things I'll need to do, but again, I am perfectly fine not rushing material, as I would rather us